Okay. So, I think we'll get started. So the first homework assignment on chapter 19. It's up on Pearson's MyLab and Mastering. I shuffled the dates a little bit. It is due on the 30th. It is now available. I have apparently made sort of typo in the availability. It was set up to be available much later than it should have been. I fixed it. The link is on Blackboard in the homework section. It's also, going directly under Pearson's. You should be able to see the chapter 19 homework. Because I had screwed up the availability, I moved it back to the 30th. I shuffled some of the other dates around until they're a little bit later. And all three of you have gotten on to Pearson successfully. Because I saw you there when I was looking. So we were discussing Coulomb's law. Coulomb's law is the law that describes the force between charged points, particles. So yes, so force is K, the absolute value of Q1, the absolute value of Q2 over radius squared. The unit, it's force, so the unit is a Newton, and K, the constant is 8.99 times 10 to the 9 Newton meters squared per coulomb squared. And the force is along the line connecting the charges. It's attractive if the charges are opposite and repulsive if the charges are alike. And Coulomb's law is stated in terms of point charges, but it's also valid for spherically symmetric distributions of charge. So any sort of ball of charge, where if you rotate it like a sphere, the charge distribution doesn't change. And then you measure the distance from the center of the sphere. And this is similar to the case for spherical mass distributions in gravity. Same thing happens. It has to do with the fact that this is an inverse square law. When you add up the forces in an inverse square law, it turns out spherical distributions act like a point in the center. So if you have an insulating sphere of radius 1.12 meters and it has a uniform surface charge density, so it's a ball, the surface has the same charge density everywhere of 5.5 microcoulombs per square meter, and a point charge of 0.83 microcoulombs is at a distance of 0.44 meters from the center of the sphere. And we want to find the magnitude of the force exerted by the sphere on the point charge. Oh yeah, that statement about charge distributions acting like point charges, that only applies if you're outside the charge distribution. If you're inside the sphere, all the stuff that's outside of you cancels out. But we'll talk about that in a little bit. So this sort of situation, we have a sphere of charge. We need to figure out how much charge is on this sphere, so we know the density on the surface. So for this, we're going to need the surface area of a sphere, which is 4 pi r squared. And figure out the density, and then we can figure out the force from Coulomb's law. So we'll start. We have Coulomb's law is going to be K times the charge of the sphere times the charge of the point over that radius, little r squared. But the charge of the sphere is going to be 5.5 microcoulombs per square meter times the area of the sphere, surface area of the sphere. And that's 5.5 microcoulombs per square meter times 4 pi r, the radius of the sphere squared. So that's 5.5 microcoulombs per square meter times 4 pi times 0.12 meters quantity squared, which comes out to 0.995 microcoulombs. So now we know how much charge is on the sphere. We know the charge of the point charge. We know the distance between them. And we know what K is. So we can just plug in our numbers. 8.99 times 10 to the 9 Newton meters squared per coulomb squared times the charge of the sphere, 0.995 times 10 to the minus 6 coulombs, times the charge of the point particle, 0.83 times 10 to the minus 6 coulombs, divided by the radius squared, 0.44 meters, quantity squared. And that comes out to 0.038 newtons. And that would be repulsive because these are both positive charges. So that was Coulomb's law that we finished up. Let's talk about the electric field. Often we have some set of charges or some structure, and we want to know what force it's going to apply to some random charged particle we put in. And it turns out this concept of an electric field is really useful. And the electric field is basically just, you ask the question, what would the force be on some test charge if I dropped it at some point? So the electric field is the force on that test charge divided by the charge of that little test charge. So this serves to allow the electric force to be measured, but it's not large enough to create any significant force on any other charge. So what force it would experience divided by its charge. The units of the electric fields are newtons per coulomb. So force over charge, because it's, the electric field tells you what force you get. If you multiply it by the charge of something, the force you get will be the electric field times whatever the charge of that object is. And the electric field from a point charge is fairly straightforward. So if we know the electric field, the force on any object, if you know the electric field, is just the charge of that object times the electric field it's in. And the direction of the force depends on the sign of the charge. So positive charges will have a force in the direction of the electric field. Negative charges will be in the opposite direction. So it's in the direction of the field for a positive charge, opposite to it for a negative charge. The electric field of a point charge points radially away from a positive charge and towards a negative charge. So if you have some point charge here, the electric field it is creating will point away from it if it is positive and towards it if it is negative. And for a point charge, the electric field is K Q over radius squared. And you can put a little R hat for the direction. That just means radially from the point charge. Basically, all I did is I took this force and divided by our test charge. And you're just left with the charge. And the electric field goes out from positive charges and into negative charges. So the force will be, the electric field will be out from the positive charge and in negative from a negative charge, which is why there isn't an absolute value for it, because it has a sign. The electric field, KQ over radius squared. And it's going out for positive charges and in for negative charges. And just like electric forces can be superimposed as vectors, electric fields can as well. And you just add them as vectors. So if I want to figure out the electric field from these two positive charges, I have one electric field going this way, one electric field going this way. When I add those vectors together, I get a net vector pointing this way. So if I drop the charge right here, it would head along the positive x direction. And vectors can be added by either adding their components or adding them graphically and so on. So let's find the electric field produced by a point charge of 3 microcoulombs at a distance of 1 meter and at a distance of 2 meters. This is fairly straightforward. Electric field is just KQ over radius squared. So at 1 meter, K, 8.99 times 10 to the 9 Newton meters squared per coulomb. Squared times 3 times 10 to the minus 6 coulombs. That's 3 microcoulombs divided by 1 meter quantity squared, or 1 meter squared, is 2.7 times 10 to the 4 newtons per coulomb. And units for electric field is newtons per coulomb. Eventually, you'll also learn that that is the same as voltmeters, but so sometimes you'll see it written as voltmeters, but newtons per coulomb is what we're going to use for now. Electric field, 8.99 times for 2 meters, it's 8.99 times 10 to the 9 Newton meters squared per coulomb squared, times 3 times 10 to the minus 6 coulombs, times 2 meters squared. I should add parentheses on these. Sorry about that. I just want to make those a little clearer. Which is 6.7 times 10 to the 3rd newtons per coulomb. 4 times it's a quarter as much. And if you dropped like a 1 microcoulomb charge at 1 meter, the force would be the electric field times the charge. So 2.7 times 10 to the 4 times 1 times 10 to the minus 6. So 2.7 times 10 to the minus 2 newtons. So here we have two charges, Q1 and Q2, that have equal magnitudes. So the charges are the same signs, but we don't know what the signs are. They're placed at these 2 points, equal distances above and below the origin. And the net electric field at point P here is upwards. So the question is, what are the signs of these charges? Is Q1 positive and Q2 negative, Q1 negative and Q2 positive, or Q1 and Q2 both positive or negative? So given that the electric field here points straight up, remember electric fields point out from positive charges and in towards negative charges. what do you think the signs of Q1 and Q2 here are? You think they're both positive? So this is the total, the sum. And what do you think? Q1 here, do you think this is positive or negative? Who thinks it's positive? And who thinks it's negative? Okay. And then Q2, positive or negative? You're saying negative. You're saying plus minus. And you? Also plus minus? So, almost correct. You are backwards. So if it was plus minus, I'll show you what you get. Remember, electric fields go away from positive charges and towards negative charges. So this is E1, this is E2. You add these two together, you get E net. It will be pointing directly down. The actual answer is the opposite. It is minus plus. This is E2. This is E1, and E net is the sum. You draw those the right line, but and if they were good, so this is minus plus, down would be plus minus, this way would be plus plus, this way would be minus minus. So you can't get all four directions by messing around with the signs. But in this case, it is minus plus. Remember that it's going to go away from positive and towards negative. So it's sort of going away from positive towards the minus. That's up. So here we have two equal charges of plus 2.9 microcoulombs on the corners of a square, half meter square. And we want to find the magnitude and direction of the field at the third corner. So we're going to be adding up the vectors here. We have E1 here, E2 here, E net here. Let me just check that I actually, yeah, I did do the work. So for this, we can break this down. We want to figure out what E1 is and what E2 is, the size of them, and then their directions, and then add them. The electric field is going to be K times Q over radius squared. So the magnitude of electric field 1 is going to be K over Q1 divided by square root of 2R, square root of 2 times the size of the box, squared. So we square root of 2, we get 2. It's 8.99 times 10 to the 9 meters squared per coulomb squared times 2.9 times 10 to the minus 6 coulombs. That's the 2.9 microcoulombs divided by 2 times 0.5 meters squared, which comes out to 5.21 times 10 to the 4 newtons per coulomb. And then this is also at a 45-degree angle. E2 is going to be K times, okay, that would be Q2 over radius squared. There's another typo there. Let me just fix that. Not that it actually matters because they're the same, but it's gonna bug me. So so that's 8.99 times 10 to the 9 meters squared times 2.9 times 10 to the minus 6 coulombs over 0.5 meters squared. Or twice as much as E1 at 1.04 times 10 to the 5 newtons per coulomb. Now, when we combine them, we have to add these as vectors. So E1 is 5.21 times 10 to the 4 newtons per coulomb. E2 is 1.04 times 10 to the 5 newtons per coulomb. But E1 is at a 45-degree angle. So E1x is 5.21 times 10 to the 4 newtons per coulomb times the cosine of 45 degrees, which is 3.68 times 10 to the 4 newtons per coulomb. E1y is also 3.68 times 10 to the 4 newtons per coulomb because it's at the sine of 45 degrees, which is the same. E2x is 1.04 times 10 to the 5 newtons per coulomb. E2y is 0. And then we can just add these up. The x component of the sum is 3.63 times 10 to the 4 newtons per coulomb plus 1.04 times 10 to the 5 newtons per coulomb, or 1.14 times 10 to the 5 newtons per coulomb. The y component is 3.68 times 10 to the 4 newtons per coulomb. So the magnitude is EX squared plus EY squared, all square rooted. So 1.41 times 10 to the 5th squared plus 3.68 times 10 to the 4 squared, all square rooted, gives you 1.46 times 10 to the 5th newtons per coulomb. And the direction is going to be the inverse tangent of EY over EX. The inverse tangent of 3.68 times 10 to the 4 over 1.41 times 10 to the 5th, which is 14.6 degrees, is that. So there's a bunch of calculations, but it is reasonably straightforward. You break it into components and add up all the components, and then recombine. Any questions? Now, one of the ways to visualize an electric field is to draw electric field lines. Electric field lines are lines in the direction of the electric field. They point in the direction of the field vector at every point. They start at positive charges or infinity. They end at negative charges or infinity. And they're more dense where the field is stronger. They're always sort of an approximation. So here, if you have a charge of Q, you could draw these field lines going out. Here we have a charge of minus 2Q, so we have twice as many field lines going in. If you're drawing it two-dimensionally, it's never going to quite be exactly right. They're never quite perfect. But that's the general idea. They show you the strength of the field by their density and the direction of the field by how they go out or go in. And they go out of positive charges and into negative charges, or off to infinity. So if you have two charges interacting, you have, so here you go out from the positive and into the negative. You can see they sort of curve around. Here we have out from the larger positive and then into the negative. And here we have two repelling charges. They go out and then away from each other with no charge in the middle. Lines are less dense where the field is weaker. The field is not necessarily zero where there's no lines. And there's only one point in these figures below where the field is zero. Where do you think that is? Only one of these figures has a point of zero field. Which figure do you think it is of these three? Yep. Where do you think it is? Yep. The only point of zero is exactly in between those two. where the fields exactly cancel. Otherwise, there's always a little bit going out somewhere. If you have a whole bunch of charge on a flat plate facing another flat plate with the opposite charge, you get a very nice electric field. It's even, that's all pointing from one plate to the other and all parallel. This is a parallel plate capacitor. It's sort of like the idealized simple capacitor. Actual capacitors have to deal with that. This design is kind of awkward, but two conducting plates with equal and opposite charges. The electric field in between is this nice even constant electric field. And then you can do some calculations with it. But it's sort of a nice idealized state. This is what we'll be doing to work out how capacitors work when we start talking about things in circuits. So, electric field line. Can electric field line intersect or not intersect? Which of those following statements is correct? The electric field lines can intersect or electric field lines cannot intersect. Nope, they can't. Because if they intersected, that would imply the electric field had two values at the same location. And that doesn't make sense. I didn't write that up, but the basic idea is they can't intersect because if they did intersect, that would imply two different electric fields at one point. The only thing that sort of intersects is that they come out of positive charges or into negative charges, but that's not an intersection, it's a termination. So here we have a parallel plate capacitor. The electric field between a parallel plate capacitor is very nice and ideal. It's horizontal, uniform, and constant of magnitude E. And a small mass of object of mass 0.25 kilograms, 0.025 kilograms and charge negative 3.1 microcoulombs is suspended on a thread between the plates, as shown in this sketch. And the thread makes an angle of 10.5 degrees with the vertical. So what is the tension in the thread and the magnitude of the electric field? So if we want to work this out, we can see here where this charged particle, there is the force of gravity pulling it down, the force of the electric field pulling it to the left, and tension pulling it up and to the right. So I'll give you a few minutes to work this out. So let's start by working out what the tension in the thread is. This we can just do with static equilibrium. The total forces in the x direction is tension times sine theta minus Q times the electric field, where Q is 3.1 microcoulombs. The total forces in the y direction are tension times cosine theta minus mg. So to solve for tension, we can use the forces in the y direction. Tension is mg divided by cosine theta. So 0.025 kilograms times 9.8 meters per second squared divided by the cosine of 10.5 degrees gives us 0.249 newtons for the tension. Now we could solve for the electric field. Tension is 0.249 newtons. The electric field is going to be tension times sine theta divided by the charge. So minus 2.49 newtons times the sine of 10.5 degrees divided by 3.1 times 10 to the minus 6 coulombs. Since we're just looking for the magnitude, the signs don't matter, so we just drop the minus sign. That's 1.46 times 10 to the minus 4 newtons per coulomb. And so that is the magnitude. I mean, times to the 4 newtons per coulomb. I misspoke there. So that's the magnitude of the electric field. So here we have the electric field lines for two charges are shown here. One is the sign of charge 1. What is the sign of charge 2? And is the magnitude of charge 1 larger than charge 2 or not? So let's look at this. What do you think the sign of charge 1 is? Electric field lines are going into charge 1. So it's negative. How about charge 2? Positive. And is the magnitude of charge 1 larger than charge 2 or not? Remember, magnitude is going to correspond to how many lines are coming out. One is larger, yes, because it has more lines coming out than charge 2. Okay. We definitely have more time, so I'm going to keep going. I'd rather get ahead. So let's talk about shielding and charging by induction. So because excess charge on a conductor can move around, the charges will move so they're as far apart as possible. This means when you have a conductor, the excess charge will always end up on the surface and will spread out. So if you have a spherical conductor, it will evenly spread out over the surface. And none of the charge will be inside the volume of the sphere. What this means is that effectively, this conductor, by moving all the charge to the outside, shields the inside from that charge. So if electric fields are at rest, if electric charges are at rest, the electric field within a conductor will always be 0. So here we have a conductor with a charge in the middle. This positive charge will attract negative charges to the inside surface of the conductor to cancel out the electric field. They will push positive charges to the outside of the conductor. So there'll be zero electric field in here, and the electric field outside will resume as if the charge was right here. So what that means is that if you have a conductor, the area inside of a conductor is shielded from the electric fields from outside. You may have heard of something called a Faraday cage. A Faraday cage is a box made of conductor designed to shield the inside from electric fields on the outside. And because the electric field always ends up zero inside, the electric field is always perpendicular to the surface of a conductor. Because if it wasn't, the charges would move along the surface. So if you have a conductor here in an electric field, charges will move so that the electric field inside is zero and the electric field is perpendicular at the surface. Because if it wasn't perpendicular, the charges would move until it was. And because of this, you end up with the electric field being stronger where the surface is more sharply curved. This is actually part of why things like lightning rods are pointy. They actually help generate a larger electric field and help prevent the buildup of charge. They can discharge more easily and help keep your house safe. The electric field is stronger when the surface is more sharply curved. So, charge will concentrate in corners and pointy places. And if you have a conductor, you can charge it by induction if you have a way to ground it. Basically, what you can do is you can bring a charged rod or a charged object up to the conductor. It will pull opposite charges towards it, push like charges away. Then you can ground the far side and get rid of those like charges. And the whole thing will be left when you remove your charged object with. So here we take a negative rod up to the conductor, it pulls positives towards it, pushes negatives away. We ground the opposite side, those negative charges disperse into the ground. So when we remove the ground, the whole thing is now positively charged and they will distribute over the surface. And this allows, so when we ground the conductor, like charges will leave the conductor. And if the conductor is then isolated before the rod is removed, only the excess charge pulled towards that rod will remain. So if you had a metal cube that was charged, where on it would you get the strongest electric field? Well, if I had charged this metal cube, where would I get the strongest electric field? What? So the whole thing, I'm just going to add a positive charge to the whole cube. Where am I going to get the strongest electric field? Remember, electric field is strongest where it's most sharply curved. So at the corners, you get the strongest. Yeah. And here I have two spheres connected with a wire. They are charged. So would you expect the field near the surface of sphere 1 or sphere 2 to be the strongest? Yeah, that's part of it. It's actually because it's more sharply curved. But it's a similar principle. Yeah. Okay, so I need to make a loop. So let's talk about electric flux. Electric flux is a measure of the electric field perpendicular to a surface. So if I have a surface, one way you can think about it is to think about shadows. So here, I'm blocking a lot of light when the light is coming in perpendicular to this. But if I get it parallel, barely anything makes it through. So electric flux, if you have a flat surface, electric flux is defined as electric flux, which is a capital Phi, is the electric field times the area of the surface times the cosine of the angle between the normal to the surface, the perpendicular to the surface, and the electric field. So if the surface is perpendicular to the electric field, you get maximum flux. If it's parallel to the electric field, you get zero flux. And the units are Newton meters squared per coulomb. And so this seems sort of a weird thing, talking about how much electric field is going through a surface. But it turns out it's one of the ways you can figure out what electric fields are. Because if a surface is surrounding some charge, the amount of electric field coming out of it, the flux, corresponds to the amount of charge that's inside it. And this is what's known as Gauss's law. So electric flux is a measure of how much electric field is going through a surface. And Gauss's law says that if you have an arbitrary surface and you work out all the flux going out of that surface, from the inside out, that will equal the total charge over this number epsilon naught. And epsilon naught is 1 over 4 pi k, or 8.85 times 10 to the minus 12 coulomb squared over Newton squared. Sometimes you will see K, the like Coulomb's law here, or this equation written with epsilon naught instead of K. One over 4 pi epsilon naught is also equal to K. So you'll sometimes see Coulomb's law written as 1 over 4 pi epsilon naught times Q1 over. Right. This is, I believe, the free permeativity of space is what it's called, or something like that. And so the total flux is equal to the charge divided by the enclosed divided by epsilon naught. Which means if you have something that's nice and symmetrical, and you know the electric field should be nice and symmetrical, you can use Gauss's law here to work out what the electric field should be. So you can actually generate this electric field law from a point charge from Gauss's law. So if you have systems with relatively simple configurations, nice and symmetrical, so you sort of know which direction the electric field has to point, you can work out the electric field using Gauss's law. Now here we have some funky surface, S. It's going to have positive electric flux on this side and negative electric flux on this side, because it's, when electric field lines go in, you get negative flux. When they go out, you get positive flux. So what do you think the total electric flux of this weird region S here is, if this is the only charge? Okay, so we have this surface S. This is a weird surface S. It has electric field lines passing through it from this charge. Positive flux on this side, negative flux on that side. Because when the lines are going in, it's negative. When they're going out, it's positive. What do you think the total flux through the whole surface is? Do you think it's positive, negative, or zero? Yes, but so on this side, on the inside here, they're going into this region S. So the blue region is S. So they're going in here. When they enter the region, they have negative flux. When they exit it, they have positive flux. It is zero because there's no enclosed charge. You can use Gauss's law to work out what the total is. So Gauss's law says if you have some surface that encloses a charge, the total flux out of that surface will be the enclosed charge divided by epsilon naught. And in this case, there's no enclosed charge. So so the total flux equals zero. And what it is that what goes in and is negative, then goes out and is positive, and they cancel out. So here we have a cylindrical surface. And Gauss's law, remember that for any surface, flux is going to be the electric field times the area times the cosine of the angle of the normal of the surface with that surface. So at the end cap here with area A, that angle is 0. Around the edge of the cylinder, that angle will be 90 degrees. In this parallel plate capacitor, each plate has a charge per unit area of magnitude sigma. And we want to calculate what the electric field inside this parallel plate capacitor is. So we can use Gauss's law. We know that the total flux through the surface will equal the total charge enclosed by that surface. And so we can think about the surface in a few parts. So the total flux is going to be the charge over epsilon naught. That total flux can be broken into 2 parts. Well, 3 parts. The flux through this end cap A here that's in the air in the middle of the capacitor. The flux through the end cap A here that's inside the metal plate of the capacitor. And then the flux through the cylindrical sides of the surface. And that flux is going to be electric field times the area times the cosine of the angle between them. The flux through the end cap A, which is sigma times the area over epsilon naught, will equal the electric field times the area times the cosine of 0 degree. The flux through the end cap inside the metal plate is 0 because there's no electric field. And the flux through the sides of the cylinder is also 0 because that is parallel to the electric field. So the angle of the sides of the cylinder, the angle is 90 degrees. So that cosine is 0. So the total flux is electric field times A times the cosine of 0 degrees. So sigma times area over epsilon naught, because cosine of 0 is 1, equals electric field times area. Area cancels. Electric field is sigma over epsilon naught. Because for this cylinder, at the ends, we're perpendicular, but along the sides, we're parallel, so there's no flux. And inside the plate, there's no electric field. The electric field only exists outside. Are there any questions about this? And here we have a similar problem where we're finding the electric field of a line of charge with a charge per unit length of lambda. Here, if you think about the electric field, it has to go out in all directions from that line of charge. And it's going to be perpendicular to the line. Does that make sense? I mean, if you have like a straight line of charge, the electric field isn't going to be pointing along the line, it's going to be pointing perpendicular. You can think about it that nothing would change about the charge if you flipped it around, so it can't be pointing forward or back. Because if you flipped it around, it would be pointing the other way, but nothing has changed about that line of charge. So here, if you draw a cylinder that is length L and radius R, the ends are going to be parallel to the electric field, so they won't have any flux. The surface of the cylinder with area, the sides of the cylinder, sides, the flux is going to be electric field times the area, which is 2 pi times length times the cosine of 0 degrees. At the ends, the flux will be whatever the electric field is, which varies, times the area, which is 0 pi r squared, but more importantly, times the cosine of 90 degrees. So this will be 0. So our total flux is going to be the charge enclosed divided by epsilon naught. That flux is going to be electric field times area times cosine of theta. The area that is relevant is the side of the cylinder, which is 2 pi r times the length. The total charge is going to be lambda times the length. So lambda times the length over epsilon naught equals electric field times 2 pi r length times the cosine of 0 degrees. So lambda over so if you cancel length, length cancels here. So lambda over epsilon naught equals electric field times 2 pi r. because cosine of 0 degrees is 1. So the electric field is lambda over 2 pi r epsilon naught. And here you can see how if we do a point charge, the area of a sphere is 4 pi r squared. Hence 4 pi epsilon naught r squared. And I think I will stop there today. I'll see you guys next week. And I'll shuffle some things around. Okay? So have a nice day. Oh, we're just about, actually, we have one more problem in chapter 19. We might as well just finish it. So what's the electric field inside an empty metal box? What? So if it was charged, it would be strongest at the corners, but we're inside this metal box. So the electric field, the charges will move around on the surface to make the conductor have 0 electric field inside it. So what would the electric field be inside that empty box? You could also think about it in Gauss's law that you can, if you draw a surface anywhere inside the box, the charge it encloses is 0. It's empty. In an empty metal box, the electric field is 0 because the metal effectively shields from the electric field. So just going over a summary of chapter 19, electrons have a negative charge, protons have a positive charge. That magnitude of that charge is 1.6 times 10 to the minus 19. The unit of the charge is the coulomb. Charge is conserved and quantized in units of E. Insulators don't allow electrons to move between atoms. Conductors allow conduction electrons to flow freely. The force between electric charges is along the line connecting them. Like charges repel, opposites attract. Coulomb's law gives the magnitude of the force. K times Q1 times Q2 over the radius squared, where K is this constant. The forces exerted by several charges will add as vectors. And a spherical charge distribution behaves from the outside as though the total charge were at the center. Electric field is the force per unit charge. For a point charge, electric field is KQ over radius squared. And electric fields created by several charges add as vector. Electric field lines help us visualize the electric field. Field lines point in the direction of the field. They start on positive charges or infinity. They end on negative charges or infinity. They're denser where the electric field is denser, bigger. Parallel plate capacitors are two oppositely charged conducting parallel plates. The excess charge on a conductor is on its surface. The electric field within a conductor is 0 if charges are static. And a conductor can be charged by inductions, can be grounded. The electric flux through a surface is electric field times area times the cosine of the angle. Gauss's law is that the total electric flux through a surface, out of a surface, is the charge contained over epsilon naught. And epsilon naught is 1 over 4 pi k, or 8.85 times 10 to the minus 12 coulomb squared, meters squared. That was chapter 19. So see you next week when we'll continue with chapter 20. Mm-hmm. Yeah. Oh, stop sharing.